Okay, so welcome back. Hi everyone. So we've onto a new topic today. We're onto the topic of linear programming. Okay, so we've spent the last 8 lectures, I guess, working on kind of least squares problems and quite a bit of various aspects of numerical linear algebra. Today we're changing tack a bit and we're moving on to this topic called linear programming. This may be something you've seen before. You possibly did it even in high school, where you had you drew on a number of constraints on a picture and you tried to find the best value of some function by going around the edges of it. Okay, so it may be vaguely familiar to you, but what we're going to do this course is actually do it properly. So how do you solve a linear program when you've got lots of variables and lots of constraints, and how do you do it algorithmically rather than just drawing a picture? Okay, now there are a few ways of teaching this, because linear programming is actually just a special case of a non-linear optimization problem. So what I'm going to do first is I'm just going to introduce you to the idea of a general optimization problem, and then we'll start talking about linear programming as a special case of that. Okay, so we'll come back to this definition later on, because this is not the only type of optimization problem we're going to solve in this course, but a general optimization problem in standard form looks like this. Okay, we minimize over x in some space an objective function f naught of x subject to a number of constraints. Okay, and these include inequality constraints. Okay, and we can have any number of those. And equality constraints. And likewise we can have any number of those too. Okay, so just a little bit of terminology. Now one thing with optimization is you'll find there's quite a few different pieces of terminology we've got to pick up. So just a few things we need to note here. We are trying to minimize what's called the objective function. Okay, so that's that function f naught of x subject to a number of inequality constraints. Okay, and those are the fi's of x being less than or equal to 0, and a number of equality constraints. I should make those blue. Okay, and they're the ones hi of x equals 0. Okay, a few other things. We say that a point x star is optimal if there are no other feasible points with f naught of x is less than f naught of x star. Okay, now I probably should have mentioned feasible points first, so let's just shift that down a bit. Go down there. Points, if you're writing your notes, it'll still be fine. So points that satisfy all the constraints are called feasible points. So points x satisfying all constraints are said to be feasible. Okay, so if your point x basically satisfies all of the fi ones and all of the hi ones, then your point is feasible. And the set of all feasible points is called the feasible region. Okay, so we're only interested in looking at the objective function value for points that satisfy the constraints, and the set of points that do satisfy all of those constraints is called the feasible region. Now, often in an optimization problem, finding a point that's feasible is not as trivial as it sounds. So actually finding out what the feasible region is, or finding a point in it, can be quite a significant problem in itself. Okay, and actually we'll look at how to solve that problem as part of our linear programming topic. Okay, so back to our optimality. A point x star is optimal, I think that should have been blue, if there are no other feasible points that have a lower objective value. Okay, so that's a general optimization problem. So all this terminology holds true for all optimization problems. Okay, now, but what we're going to be looking at are linear programs. So basically, a linear program is an optimization problem, except that these various functions take on a particular form. So let's just write down what that form is. Linear programming problems. Okay, so all of the functions fi and hi need to be affine. Okay, now what that means is basically linear plus a constant. Okay, so the general LP, or linear program, therefore has the form, once again, minimize over x, C transpose x plus D. Okay, so our objective function is linear, that's the C transpose x piece, plus a constant, subject to inequality constraints, and they can be written like this. A matrix times x is less than or equal to a vector, so there are a number of, each row of this matrix G and entry of h corresponds to one inequality constraint, and a number of equality constraints, which can be written as ax equals b. Okay, now that's completely general. We can also solve maximization problems too. So maximization problems also fit into the same framework. So we can also solve maximization problems too. How? Well, we'll just note that the maximize over x of f naught of x is equivalent to minimizing, equivalent, see if I can write that down properly, equivalent to minimizing negative f. Okay, so if we have a maximization problem, we can turn it into a minimization problem by just multiplying the objective by -1. Okay, so that's a general LP. One other thing to note, we don't really even need this constant here, because minimizing our problem is not really it's going to be the same minimum, plus if we take this d off as well. Okay, it's just a constant that's added on to every possible value of the objective function. So minimizing our function, we can replace the objective by C transpose x, if it's only x that we're interested in. Okay, so why don't we just have a sample? See if we can fit it into our framework. So example, maximize over x, x1 plus 2x2. Okay, so there's our objective, is just x1 plus 2x2. We want to make that as big as possible. Subject to the following constraints. x1 is greater than or equal to 0, x2 is greater than or equal to 0, you'll notice that you often have this non-negativity constraint on the x variables because they often correspond to some kind of physical quantity. It can't be negative. We've got another one, negative x1 plus 2x2 is less than or equal to 4, and 3x1 plus x2 is less than or equal to 9. Okay, so why don't we just, as a little exercise, see if we can put it into this standard form here. Okay, I'm actually going to give that an equation number, just so that I can make sense. So put it into form of 9.2. Okay, and I'll give the general purpose optimization problem equation number 9.1. Okay, so how do we do that? Well, first thing we have to do, we have to turn it into a minimization problem. Okay, and we have to write it as C transpose X plus D. Okay, well, so we're going to minimize over X, C transpose X. Okay, well, if we were leaving it as a maximization problem, then C transpose would be the vector 1, 2 times X, which is an R2. Okay, but because it's a maximization problem, we need to make these things negative. Multiply the objective function by negative 1. Okay, subject to, well, we've got inequality constraints and we've got equality constraints. There are no equality constraints, so we're just going to write down the inequality ones. So the first one, well, I've got 4 of them, so I'll set up my 4 by 2 system. First one says the x1 has to be greater than or equal to 0. Okay, so if we want it to be a less than, we could also write negative x1 is less than or equal to 0. Likewise for the second one. Okay, so it's very easy to turn a greater than or equal to inequality into a less than or equal to 1. Once again, we just multiply the whole thing by negative 1. So we get negative x1 is less than or equal to 0. We get negative x2 is our second one, is less than or equal to 0 as well. We get negative x1 plus 2x2 is less than or equal to 4. And we get 3x1 plus 1x2 is less than or equal to 9. Okay, so we'll just give in the matrices, the vectors, their names. So C is the vector negative 1, negative 2, because this one here is C transpose. And this matrix here is our G, and this matrix here is our H. Okay, so it's pretty straightforward to write an LP into this very general form. Okay, so let's have a look at this problem. Let's keep going with it and see if we can sketch for ourselves the feasible region. Okay, so hopefully you've got that written down on a piece of paper because I'm going to get a blank screen. What I want to do is I want to sketch the feasible region. Okay, so set up some axes. Okay, so the first constraint, I should get these little constraint numbers. 1, 2, 3, and 4. Okay, so my first constraint says that x1 is greater than or equal to 0. Okay, so this is my x1 axis along here, and this is my x2 axis up here. x1 is greater than or equal to 0 just means that we're in the right half plane here. So the way we indicate this is we shade out the region that's not satisfied by our constraint. Okay, so this one here is constraint 1, and I basically shade in to represent everything to the left of the x2 axis. Likewise, the second one is that x2 is greater than or equal to 0 as well, so I'll do the same thing for that one here. I'll shade out the area violated by the constraint. Number 2. Okay, what's the third one? The third one is negative x1, I'll just make a little quick jot of that, negative x1 plus 2x2 is less than or equal to 4. Okay, so we sketch the line. Well, what's it going to look like? Just for sanity's sake, we'll draw the line x2 equals half x1 plus 4. Sorry, plus 2 it'll be. So let's draw that line on. So it's going to go have a y-intercept of 2. Just put some numbers on here. 1, 2, 3. 1, 2, 3. Half x1 plus 2, that looks like, well, it's going to go through the point 2, 3, isn't it? See how accurate I can draw this, just there it goes. Okay, and what is the part violated by that? Well, the corresponding inequality is x2 is less than or equal to that line. So the part violated is the part above the line here. Okay, so that there is my third constraint. You can see that I'm building up, I've only now got this area here that satisfies all of the constraints at the same time. Okay, so our last constraint was, just get rid of my working. Last constraint was 3x1 plus x2 is less than or equal to 9. Solving that for x2, just to make it easier to draw, that gives us x2 is less than or equal to negative 3x1 plus 9. Okay, so that's going to have a slope of negative 3. It's going to therefore intercept my x-axis at 3. So it's going to go there. It's going to also come through this point 2, 3. And my y-intercept is going to be somewhere way up there at, I don't know, at 9, sorry. Okay, so let's see if I draw that one. There it goes. Close enough. And x2 is less than or equal to that, so we'll shade out the area violated by that constraint. Okay, so our set of constraints has given us what we call a feasible region. Okay, so the region that satisfies all of the constraints. Now, for a given set of constraints, you may even not have a feasible region. You could see that if I had another constraint that was something like, well, even x2 is less than or equal to 0 as well as greater than or equal to 0, then in that case I'd have an empty, or almost empty, feasible region. Okay, so we need to bear in mind that although these pictures look very nice and have a feasible region, it's possible that a set of constraints that you write down may actually conflict with each other in such a way that you don't even have a feasible region. Okay, I'm just going to label these points. We'll call this one O, we'll call this one U, call this one S, and we'll call this one T. Okay, so the feasible region is the region OSTU. Okay, so we'll come back to this example soon, but we're going to basically narrow down this definition of a standard form. So I've said that any linear programming problem can be written in this general form, but it turns out this is not actually the most useful way to write down an LP. There are two special cases which have their own forms. Have their own names. Okay, and what are these? Well, we have Inequality Form Lp. Okay, so this one looks like minimize over x of C transpose x, subject to AX is less than or equal to B. Okay, and so the only thing we've got here are inequalities. We don't have any equality constraints, so that one there is called Inequality Form Lp. The other special case is what we call Standard Form Lp. Okay, and this one looks like minimize over x, C transpose x, subject to a set of equality constraints and a set of non-negativity constraints. Okay, the reason we have these two special forms is that the algorithms that have been developed to solve linear programming problems basically need, well, they don't need to, but originally they did. They pretty much need to have the linear program specified in the standard form. Okay, they were designed to solve these types of linear programs. Now it turns out that you can turn any linear program into a linear program in standard form. Okay, so we're going to have a look at how you do that, and then we'll do it to our example. So conversion to standard form. Okay, so we can take our very general linear program. So our general LP, if you remember, was minimize C transpose X plus D subject to, sometimes I just write this left-hand bit as a shorthand, Gx is less than or equal to H and Ax equals B. Okay, now if you look at our standard form, we don't want to have any inequality constraints apart from our non-negativity one. So the first thing we do is we take this Gx is less than or equal to H and we say, okay, I'm just going to add some variable S to that and make it equal to H instead. So for example, if you've got the just in one variable, if you've got the constraint 3x is less than or equal to 5, then you could rewrite this as an equality by saying 3x plus s equals 5 and s is greater than or equal to 0. Okay, so you may need to pause it if you want, but have a think about why it is that these two statements are equivalent. So we take an inequality, we basically work out the amount by which the inequality is violated, and we just give that a name. We call it S. S has to be positive, otherwise that won't make sense. But these two things are equivalent. So what we do is we basically, for every single one of our inequalities here, we define one of these variables S, and we call them slack variables. So we introduce some more terminology, slack variables. Okay, they take up the slack of the inequality, how much they're violated by, how much they're not satisfied by, and one for each inequality. Okay, which turn the inequalities into equalities. Okay, so we get this additional piece. So LP becomes minimize over X, C transpose X plus D. I'm actually going to get rid of the plus D because we don't need it. Subject to Gx plus S equals H and Ax equals B, and now S is greater than or equal to 0. Okay, so that's an equivalent linear program, and we've taken these inequalities and we've now turned them into equalities. Okay, so is this finished? Are we done? if we look back at what our standard form should look like, subject to ax equals b, we've now got only equalities, that's fine. X is greater than or equal to 0. We haven't solved that problem yet. Okay, we've only got that our slack variables have to be non-negative. We haven't got that our x's have to be non-negative. So how do we deal with that? Well, once again, we just introduce more variables. So when we're turning a linear program into standard form, we're increasing the number of variables that we need to describe it. Okay, that's not usually actually a problem, but it's just something you need to be aware of. We're increasing the number of variables. We're not just minimizing over x anymore. So I guess you'd even say this is minimizing over x and s. Okay, so we need to express x as the difference of two non-negative variables, x plus and x minus. Okay, so we write x equals x plus minus x minus. Okay, and x plus is greater than or equal to 0, and x minus is greater than or equal to 0. Make sense? So, for example, if x is equal to negative 3, if x equals negative 3, then one way you could have that is you could have x plus equals 0, x minus equals 3. Both x plus and x minus are non-negative. To take them away from each other, and you get x equals negative 3. Okay, note it's not the only way. You could also have x plus equals 1, x minus equals 4, etc. Okay, so we've got these extra variables, so let's just plug them into our linear program. So the LP now becomes minimize C transpose X. Okay, so now we're going to have, I'm just writing X here kind of as an abusive notation to include X plus, X minus, and S. Minimize C transpose X plus minus C transpose X minus. Okay, I'm just replacing X by X plus. I'm just basically plugging this equation here into the LP. And subject to, let's see, gx plus minus gx minus plus s equals h, still an equality constraint. Okay, and the other piece, ax plus minus ax minus equals b, and non-negativity. We now have all the variables must be non-negative, and s is greater than or equal to 0. Okay, so it doesn't quite look like it, but that is a linear program in standard form. Okay, so let's just, why don't we just write it as to make it, just to convince you that's true, I'll write it in this block matrix form here. So we could also write like this, minimize over x, C transpose. Okay, what's C going to have to be? Well, C is going to have to be C, negative C, and 0, transpose. In fact, I'll write it as a row vector. C transpose, negative C transpose, and 0 times x. Okay, so I'm just saying that x is x plus, x minus, and s now. Subject to ax equals b. Okay, we've got quite a few of these things to deal with. So we've got g, that's what multiplies x plus. We've got negative g, multiplies x minus, plus s, So that will be an identity. X equals, well, we're going to have h for that bit. Then we've got the ax equals b1, so we're going to have ax plus, negative ax minus, and no s's times x equals b. And x is greater than or equal to 0. Okay, so that is our linear program in standard form. So there'll be a bit of practice of these in tutorial, converting general linear programs into these special ones in standard form. Now the algorithm that we're going to look at to solve linear programs, we're basically going to develop it as an algorithm for solving standard form linear programs. So it's quite important that you understand how to actually do this. Okay, so let's just return to our example again and convert it into standard form. Example revisited. Okay, so we had, what do we have? Where's it gone? Here it is. We had minimize over x, negative 1, negative 2, x, subject to. Now I'll just write out that we actually had the non-negativity constraints in there already, which is really handy. So we don't need to worry about the x plus and x minus bit. Less than or equal to 4, 9, and x was greater than or equal to 0. I'll separate them out this time. Okay, so all we have to do to make this in standard form is we just have to introduce a slack variable for each of these constraints. So negative 1, so negative, let's write them out in full. Negative x plus 2x2 less than or equal to 4. That's going to go to negative x1 plus 2x2 plus s1 equals 4. And our second one, 3x1 plus x2 less than or equal to 9, that's going to become negative, 3x1 plus x2 plus our second slack variable s2 equals 9. So we now have minimize over x C transpose x, same as before, subject to negative 1, 2, 1, 0. So it's tacking on the identity like I did just before. My variables are now x1, x2, s1 and s2 equals 4, 9. Actually, a tiny mistake there. My x's got bigger, so I just need to add in a couple of extra entries into my C transpose. Okay, and x is greater than or equal to 0. Okay, so once you've done a few, it becomes quite straightforward. It's just a bit weird the first kind of few times you see it. So we're just introducing these extra variables so that we can write down our overall system in standard form. Okay, so that's our system in standard form. Now we'll kind of revisit what you may have done before in high school. I think I did it in my year 13 stats when I was back then. So let's have a look at our picture again. So I'm just going to redraw our picture from before. So graphical solution. So I'll sketch a slightly smaller version of it. Here we had, what did we have? We had a feasible region that looked something like this. That was 2. Went through that point there, and back home again. Okay, so there we go. Here we go. Here it is. So here was our feasible region. We had these bits shaded out. And I'll just put some labels on, x1 and x2. 1, 2, 3. 1, 2, 3. Okay, so that was what we got to with our example before. Now, our objective function f naught of x equals C transpose x. Okay, so it's a linear function of x. Now we want to minimize this thing. So how do we go about doing that? So c, just remember c equals, I think it was -1, -2. Well, why don't we look at contours of f0 of x. These are where c transpose x equals constant. So why don't we sketch some of these contours on? What's the easiest way to do that? Well, we know that the contours are going to be perpendicular to the gradient. So to grad f0, if you remember your vector calculus. So the gradient of f0 of x is just equal to c. -1, -2 equals c. Okay, so if we draw a number of lines on our picture, now these will be lines for a two-dimensional case, they'll be planes, etc. for higher dimensions. They just look like lines perpendicular to the direction -1, -2. Okay, so C looks kind of like that. So my contours are going to be lines perpendicular to C. So I can sketch some of these on here. In fact, why don't I use a different colour? Might be even better. So just imagine the C vector going here, orthogonal to these contours. So these are contours of f0. Okay, and if we want to minimize our function, we want to make our objective function as low as possible. So these contours, basically, as we move along, they're either going to be getting higher or lower. They're going to correspond to higher or lower values of f0. Okay, well, we know how to do that too. You know the gradient, that's the direction of maximum increase of f0. So if we're sitting on a contour and we want to make f0 go upwards, then we travel along the direction c. Okay, the gradient is c everywhere, so we travel along that direction c, and that will make our objective function value go up. But we don't want that. We want our objective function to go down. So we want to travel on our diagram as far as we can in the direction -c. Okay, so just looking at our picture, the furthest away point, or the furthest direction, the farthest we can go in the direction -c, is this point here. So that's the vector -c, and this point here is my optimum. Okay, x star is the point in the feasible region as far as possible in the direction -c. -c. Okay, so we can do that for these simple kind of 2D cases where we can actually draw the diagram. We can figure out which point is our optimum basically by inspection. There are a few things we should actually note about this though. We can actually glean quite a few useful properties of linear programs by kind of studying this picture here. And they tend to hold in general these properties, so I'm going to start going through them. So I suppose I should finish the problem off properly. So x star is the optimum, and what's it equal to? X star equals 2, 3 is the optimum, with C transpose x star is -2 minus 6 equals -8. Okay, we can't get any lower than -8. So I suppose we should say f0 of x star equals C transpose X star equals -8. Okay, so we've finished our example. We've solved it because we could basically look at this picture. Now, one thing that you can see kind of by looking at that picture is that no matter what C is, no matter which way it goes, the optimum value is never going to be somewhere in the middle of the feasible region. It's always going to be somewhere on the outside. Okay, so we can make a few useful comments here. Properties of LP. So these are just sort of picked up from our pictorial understanding of this. So, number one, if an optimal point X star exists, then an optimal point can be found at a vertex. Okay, so it's a slightly odd way of saying that. So I'm saying that if we've got an optimal point, then at one of the vertices we'll be able to get that optimum value. So let's have a look at the picture again. In fact, yeah, I'll just really quickly sketch it here so we can see what's going on. So there was our feasible region, and we had some contours going sort of like this. No, not quite like that. Okay, and we want to travel in this direction as far as we possibly could. So the way we're thinking here is that no matter which way we orient these contours, that means no matter what our C is, we're always going to be moving to the boundary. And even if our contours are parallel to, say, this boundary line here, so if our optimum was here, this is the furthest we could go in that direction, say it was like that, then there is going to be an optimum at a vertex, namely that one and that one. Okay, so even if our contours are parallel to a boundary line, and we move right across to that boundary line or face or whatever in higher dimensions, we're still going to have optimum at least one vertex. So it's always true that we can find an optimal point at a vertex if there is an optimal point. Okay, so let's make a related statement. If there is more than one, then there is a whole line in 2D or face in 3D, etc., of optimal points. So, for e.g., for our example, if we change f naught, the objective function, to maximizing x2, subject to the same constraints, okay, so we'll look back to our picture. Maximizing x2, subject to the same constraints. Just let's go back to that picture. Sorry, I mean minimizing, not maximizing. So if our objective function was instead minimizing x2, like going as far as we can downwards, then any point along the line OU was going to be optimal. So that should be, sorry, minimizing, not maximizing. Sorry. Then the line OU is optimal. Okay, so beginning to get a good intuition for optimality like this. Okay, so a couple more things that could happen. So we're looking at all the different scenarios of optimality, really. So the problem may be infeasible. Okay, that means empty feasible region. Okay, and we can give a quick example of that. Maximize x1 plus x2 subject to x1 is greater than or equal to 0, x2 is greater than or equal to 0, and x2 is less than or equal to -1. Okay, there is no point x1 and x2 that satisfies all of those constraints, so the problem is infeasible. Okay, finally, the other thing that can happen, the problem may be unbounded. Okay, which is also bad. So if my feasible region, I was sketching it up, and I'd kind of got this and this and this, just shade those out like I was doing before. Okay, and my contours made me want to go this way, then I can basically keep going forever. There's nothing to stop f0 just decreasing and decreasing and decreasing indefinitely. Okay, in that case we say that the problem is unbounded. Okay, so e.g. maximize, that's not this picture, maximize x1 plus x2 subject to x1 is greater than or equal to 0 and x2 is greater than or equal to 0. Okay, so objective function can be made arbitrarily large. Okay, so what we've got here are basically 4 different scenarios that can happen that kind of determine what our solution looks like. We either have an optimal point, and if we do, then we can find one at a vertex. And if there is more than one optimal point, then they exist, then they're on the line. But we don't necessarily have an optimal point. Then there are 2 ways that can happen. We can either have an infeasible linear program where there are no feasible points and hence no optimal ones, or we can have an unbounded problem. Okay, there's no single optimum point. We can just get better and better indefinitely. Okay, so those are the 4 scenarios that can occur. Okay, now just looking at number 1, we're saying that an optimal point can be found at a vertex. So just quickly to finish off with, 1 suggests a strategy. And basically, because we know that the optimum is going to be at a vertex, why don't we just check all the vertices? Exhaustively. Okay, so a vertex is where n constraint boundaries intersect. So for in our case we've been working in R2, so a vertex is where 2 constraints intersect. So the number of vertices is equal to MCN combination, which you may remember is given by the following expression. So why don't we just see how many vertices we need to check? Well, it's that many. And to give you a bit of a feel for this, let's draw up a wee table. So I'll just give you a few representative values. So I'm looking at the number of constraints. So M is number of constraints. Well, I should also say that M equals number of constraints. N equals number of variables. Okay, it's 3, 5, 10, 20, 40. Usually you have more constraints than you have variables if they're inequalities. So 10, you can just work these numbers out on MATLAB or whatever, and you can see that, you're probably aware of this, they quickly become incredibly big. Okay, so typically a linear program is too big to solve by this exhaustive search method. So LPs with thousands of variables well, they're not uncommon, they're actually quite normal. Okay, so you can see that trying to check all of the vertices if we've got thousands of variables and thousands of constraints is just not going to happen. Okay, it's too many to check. So exhaustive search is computationally infeasible. Infeasible. Okay, it's fine for what we had before. But what we could have done before with our example, we only had, where's a picture of it? We only had 4 vertices. So instead of trying to figure out which way C went, we could have just checked the objective function value at each of the 4 vertices and found the best one was going to be here, and we could have been done with it. So that works for these small problems that I'm just showing you to give you the idea. But for a proper big problem, that's never going to work. Okay, so that's kind of finished our introduction to LP. Next lecture we're just going to go through a number of examples. So these are kind of modeling examples showing you what kind of physical situations you can represent with linear programming problems. But that will wrap it up for now, so enjoy your day or night or weekend or whatever it happens to be, and I'll see you at next lecture.